Yes. Because you know what? It's too bad if you're not. You are. See, this will get you all pumped up for that t-test piece of things, right? Okay. So, to the stuff that we've been working on up to now, we're focusing on comparing some sample mean against a population with a known mean and standard deviation. Okay. This is our z-tests, and this is good for sort of what it is. But and again, so if we're thinking about this, we've got some population reference, some reference population where we have a known mean, a known standard deviation. We're taking some other sample so that it's different, or taking sort of part of the known population, a sample from the known population, administering some sort of treatment to that sample, which then produces some hypothetical population with unknown parameters, right? So I go through, I take a sample of rats with known mass and standard deviation. I give them some treatment. Now all of a sudden those rats now become a different population. They're not part of this population, they're a different population. But maybe these are the only 10 rats that have ever received this treatment, but these rats represent a hypothetical population of all possible rats that would receive this treatment. And what we're interested in is whether or not the parameters of this new population that we've created are similar or different from the old population, right? And so what we're essentially asking is, if this new population has the same mean standard deviation as our original population, how likely is it to observe the data that we've observed, assuming the null hypothesis is true? Okay. So this is all well and good, but the problem is our z-tests tend to require more information than we have available to us. We need to have not only the population mean, but we need to have population variance in order to calculate our standard error. But in the vast majority of cases, we don't have access to the population variance. We don't know what that is. In some cases, rat case, we've got a well-established population with known parameters. If we're working with intelligence testing, we know what the mean and population mean and standard deviation is on this. But most of the stuff that we're looking at, we don't have this information, okay? And so a solution, how we can get around this, obviously, is the potential to use our sample variance, okay? Our sample variance, remember, is an unbiased estimator of the population variance. So the idea being is that we can use our sample variance to go through and plug in our sample variance as an estimate of the population variance and use that to calculate our standard errors. At the end of the day, any type of inferential test circles around the calculation of standard errors, okay? Chrissy, tell me what a standard error is.
Standard error is, so when we're doing confidence intervals, it tells us how far away from the mean it'll be. It gives us our lower and upper bound.
Okay, so that's our interval estimate, and the standard error goes into that. But someone help Chris out. What does the standard error represent conceptually?
Estimate the error from one estimation to the next of our.
What do you mean estimation?
Like the estimation of our underlying assumption of our analysis.
Okay,
like
so
our confidence interval and our point estimate, the difference between replication and replication.
There we go. There we go. Okay. Remember, standard error at a very basic level is the standard deviation of our sampling distribution, right? So if I were to replicate this study time and time again, how much would I expect whatever parameter I'm estimating, whether it's a correlation, whether it's a mean, whether it's a variance estimate, whether it's a regression parameter, how much would I expect that parameter to jump around, right? If my standard error is large, then I'm expecting across replications, right? Perfect replications, exact replications, I would expect my point estimate to be jumping around quite a bit. If I've got a small standard error, that means I'm only expecting this parameter to jump around. It's a much more stable estimate, right? And so then this starts to become important because remember, standard error is going in the denominator of most of our tests, right? It's saying how much of a difference did we observe between our data and the presumed value under the null over how much I expect this parameter to jump around, right? If the deviation I found is about the same amount that I would expect the thing to jump around just on its own, we're probably going to fail to reject the null, because this is just, looks like it's sort of just random error, or just sort of what we could attribute to just general error. But if what I've observed is much larger than what I would expect just based on my standard error just jumping around, we're going to say that it's likely that these are data, or we would use that to conclude these are data that are unlikely, sort of just based on sort of what we would expect jumping around. So your standard error, you can think about this as the standard deviation of your sampling distribution. You can think about this as your expected difference between any two estimated point estimates that you over an infinite number of replications. You can think about your standard error as indicating how far you would expect any replication sample to fall from the actual population parameter. Sort of these, it's very, very important. I want you guys to have a strong understanding, conceptual understanding of standard error and how this fits into our stuff. Okay. So, if we're talking about our sample variance, we know that our sample variance is an unbiased estimator of our population variance, right? And Kristen, what am I doing to make my standard, my sample's variance an unbiased estimator of my population variance?
You're pulling from, like, isn't contingent upon your, like, sampling procedures?
It is contingent on the sampling procedures, but can I calculate my population variance the same way I calculate my sample variance?
No.
Yeah, what do I got to do with it to change this?
Is it related to the sum of squares?
Yep.
Pulled from?
Yep, so I get my sum of squares, and then what do I divide that sum of squares by in my population versus my sample?
The root of the sample size?
Okay, close. That's getting a standard error. What's the difference between my sampling statistic and my population parameter? Population is over n, sample is over n minus 1, right? Because remember that we go through, we're talking about our population variance. Our sample is never going to be exactly representative of my population variance, because what is going to happen, particularly with small samples, my sample is probably going to come from the middle of the distribution. I'm not going to get those ends, right? And so what we do is we take our sum of squares, and remember our sum of squares is just a raw metric of variability. Sum of squares is a metric of variability. Variance is a metric of variability. Standard deviation is a variance of metric, is a measure of a metric of variability. But what I need to do in order to make this slight correction to my sample variance is that instead of taking my sum of squares and dividing it by the number of individuals in my population, I take this, my sum of squares, and divide it by 1 minus the number of people in my sample, right? So, CJ, if I have a very, very small sample, what's the correction going to look like on my sample variance?
What do you mean?
So if I have a small sample, and I'm comparing my sample variance with my population variance, if I have a small sample, is this n minus 1, is that going to cause a large correction or a small correction?
Large.
Large correction, right? If I divide my sum of squares by 10 versus by 9, that's going to change it quite a bit, right? What if I have a sample of 200? What's the correction on my variance there?
Lower.
It's going to be really tiny, right? Because I'm expecting with a sample of 200, I'm getting a lot more of this, right? And the correction is going to be very trivial. But if I'm working with small samples, and again, in psychology, this is our history. It's a lot of experimental small sample research. If you go back through, look at studies in the 50s, not uncommon to have sample sizes of 8 and 12 and things along those lines. So this makes a big difference, okay? So, going back to the beginning, our z-test is fine when we know the population mean and the population variance. We often don't know the population variance, and so then that's kind of a problem. So what we can do is we can take our sample variance and say, okay, we're just going to use our sample variance, substitute our sample variance for the population variance to calculate our statistics, right? And we could say, well, we know that our sampling variance, our sample variance is an unbiased estimator of the population variance because the sampling statistic is unbiased if the average value of our statistic across our applications is equal to the population parameter, right? So if we take all possible samples of a given size that could be drawn from the population, measure whatever statistic it is, calculate whatever statistic it is that we calculate, and if the average across all those samples is equal to the population parameter, we know that our statistic is unbiased. Right? And so, people follow me up to this point? So we know that our, the sample variance is an unbiased estimator of our population variance, but we run into problems when we look at the sampling distribution of our sample variance. Okay. So if we think about the sampling distribution of the mean, sampling distribution of the mean is normal, right? So if I had n equals 100, right, and this sampling distribution represents all possible samples of size 100 that I could draw from the population, I know that the expected value of the mean and I say this is the expected value of the mean, or the mean of all sample means, is going to be equal to my population parameter. Those two things are going to be identical to one another, right? And so this works nicely for when we're calculating the sampling distribution of the mean. The sampling distribution of the variance, if we're thinking about sampling distribution of the variances, all possible variances that could be calculated from a given sample size taken from the population, the sampling distribution of our sampling variance isn't normal. Sampling distribution of our variance is skewed, and the magnitude of this skew starts to get more and more extreme as we start to get very, very small samples. And if we think about this, if I'm talking about the mean, can I have samples that are above the mean? Sure. Can I have samples below the mean? Sure, right? But when we're looking at distributions like our sampling variance, can I have sampling variance that's, can I get a variance that's less than 0? No, I can't, right? I mean, if I have a sampling variance of 0, it means all the scores were identical to one another, right? So we get a lower bound of 0 on the sampling distribution. I can't get lower than 0. And so what ends up happening, particularly in small samples, is we get a distribution of sample means. So this is all possible samples, sample variances drawn from, I guess, okay, sample size 5, with a population mean of population mean 5, population variance is equal to 50. If I go through and calculate variances of samples of size 5, I get a very, very skewed distribution. Okay? And so what ends up happening is my expected value of my sampling distribution. If I take the mean of all values in this sampling distribution, that mean, my expected value of the variance, is going to be equal to the population variance. Okay? So my sample statistic or my sample variance is unbiased, because if I take the mean of all of these, it's going to be equal to the population variance. The problem is, if I go through and I pull any random sample from this distribution, Alicia, if I just grab a random sample from this distribution here, where is that sample more likely to fall? Below it. Why? There's just more of them down there, right? When I go through, because again, I'm gauging whether or not this statistic is unbiased based on the mean of the sampling distribution, right? And the average of the sampling distribution is equal to the population estimate. So my sample statistic is not biased. The problem is, for any single study that I do, any single study that PSYC conducts, the likelihood of her in that sample that you have in your hand, it's more than likely going to underestimate than overestimate, right? So where's the median and where's the mode of this distribution, Chris? See?
The mode is at about 30 to the left of the mean, and I would guess the median's to the left as well.
Yeah. This is just a skewed distribution, right? We know with the skewed distribution, the mean is going to be out toward the tail, the mode's going to be on the other side, and the median's going to fall somewhere in between there, right? So the middle score and the most frequent score in the sampling distribution falls below the mean. The mean is getting drug out towards the tail. Now the mean is equal to the population variance, but for any given random sample that I pull, I'm more likely to grab something over here than something in the tail. And because of that, because any individual sample that I pull is likely to underestimate the population variance. If I think about my standard error is equal to population variance over the square root of my sample, right? If this is too small, tomorrow, what does that do to my standard error? What's up?
It's smaller.
Yeah. It's going to reduce it, right? And if my z statistic is equal to x minus mean over standard error, if this is too small, that makes this too small. And if this is too small, what's this going to do to my z statistic? It's going to make it too big, right? And so this starts to become problematic because in our history, as we were working with small samples, the problem is my test statistic is going to be inflated. It's going to be too high because for any sample of 8 that I collect, even once I calculate and use the correction for to make my sample variance unbiased, if I'm looking at the sampling distribution of my sample variance, I'm still going to go through and underestimate on any individual sample I get, and that's going to mean my standard error is too small, which is going to inflate my z value, which means I'm going to reject the null hypotheses potentially far more than I normally would under sort of normal circumstances when I actually have an appropriate estimation of this. And this is problematic because then our test statistic, if we substitute our sample variance for our population variance, we end up with a statistic that doesn't have the distribution as the z distribution that we're using, and this is problematic. Okay. Do people see conceptually kind of what's going on with the nuts and bolts of all of this? Okay. So the solution. William Seeley Gossett, chemist for Guinness Brewing Company, working with sort of basic chemistry types of things, trying to figure out small sample stuff, right? Because I don't want to go through and have just massive production of beer because then it's all going to be bad and I'm going to waste it all. And so I'm trying to figure things out, sort of running statistics on using small samples. But the problem is my small sample stuff is all out of whack because I'm rejecting null too much. And so Gossett's work at the time, you could not, because he was an employee of Guinness, he couldn't publish under his name as part of Guinness, the whole big thing. And so Gossett published a series of papers credited for the formulation of a T distribution under the name student. So when we talk about student T, right? So this student T distribution, that's in honor of Gossett's work early on working with this. And what Gossett found was able to do is go through and determine the sampling distribution of this statistic, not a z statistic, but now a t statistic. And the only difference between the z statistic and the t statistic is that we're just substituting a sample variance in for the population variance. But when we do that, what we get is a different statistic with a slightly different distribution. And when we're taking a look at our t distributions, t distribution is actually a family of curves with different shape with each degree of freedom. So depending on my sample size that I'm working on, my t distribution is going to have a different shape. An infinite number of, now Gossett didn't sort of hand calculate an infinite number of t distributions, right? Sort of had a table, but going through and looking at our t distributions from the distribution with very, very low degrees of freedom versus as we start to get an infinite degrees of freedom, as our samples get infinitely large, what we see is this t distribution starts to approximate our z distribution or our normal curve as our degrees of freedom approach infinity. This actually happens quite a bit sooner before we hit infinity, but mathematically, theoretically, this is kind of what's going on. And so this whole development and sort of deriving this t distribution, it's a similar distribution, but it's distinct in that it's intended to deal with problems of substituting our sample variance in for our population variance with small sample research. Okay. So if I look at my sampling distribution, the sampling distribution of my t, right? Again, what my curve here is looking at is the distribution of t statistics. Again, assuming the null hypothesis is true, assuming the difference between my sample data and my sort of population parameter is equal to 0, what do I expect this t, how do I minus whatever my population mean is over the standard error? My standard error is equal to my sample standard deviation divided by the square root of n, or my variance over n, the whole thing taking the square root, sort of same thing, right? But what we see with the t-distribution is we see as my degrees of freedom decreases, my sample decreases, the critical values start to become more extreme. So in this situation, the green line here, this is my normal curve, right? But the red line is a curve that doesn't have, it's going to be a t-distribution with slightly fewer degrees of freedom. The blue line is going to be a t-distribution with lots of higher or lower, even lower degrees of freedom. And what ends up happening is these distributions, again, if I'm looking at my alpha level, I say I want to find the point in this distribution where 2.5% of the distribution is in the left tail, 2.5% of the distribution is in the right tail. What ends up happening if I go through and say in the green curve, right? Well, let's say here's my here's catches 2.5 in the one end, and here's 2.5 in the other end. If I mark that same point on the blue line, is that capturing 2.5%? No, it's a whole lot more, right? So we've got to move out. We've got to get farther out. We've got to set those stakes farther out in order to capture the bottom and upper 2.5% of the curve. And what that does is it sets our markers for rejecting the null farther out, right? And if we think about the problem with this, our problem is if we sample our, if we just use the z table and we substitute our sample variance for our population variance, it makes our standard error too small. If our standard error is too small, it makes our z-test too big. And if we're using a normal z distribution, it means we're going through and we're rejecting for it far more often than we should. In a t-distribution, if we plot this distribution out appropriately, what ends up happening is we're sort of going through and using, comparing our test statistic against a specific t-distribution that matches the sample size that we use, or the degrees of freedom that we use. That's going to set those markers out farther, making a sort of more stringent to claim statistical significance and making a correction for what we've got here. Okay? So if we go through, Alicia, and I'm looking at, based on sort of what we've talked about, if I'm looking at a t-distribution, is my critical value for my alpha 0.05 significance test, is my critical value going to be higher if I have 50 people in my sample or 20 people in my sample?
Lower?
Yeah, it's going to be lower, right? 50, and if I have 100,000, actually, it's like if I have like a couple hundred, it's going to be about the same as my z. But as my sample starts to decrease, my key statistic, my benchmarks for what I can use to claim statistical significance starts to get higher. People following the logic of this and kind of seeing how this is working out? Okay, we already went through interpretation. This is your standard error. Know what that is, okay? But again, what we see is our t-distribution. This family of t-distributions, classic example of positive kurtosis or leptokurtic distribution, which this is really cool. I would encourage all of you for your first publication, try and go through and sort of plug in an illustration. Like figure one is drawn a platypus and some kangaroos having intense eye contact, right? I don't know if you can get away with this today, but it's pretty cool. But yeah, this is actually a paper of students sort of talking about distributions, skew kurtosis, and things like that. So, all right, if we go through and take a look, so I handed out your t-distribution, or your t-tables last time. You can find these in a statistics textbook. But again, what you'll see, and the one I gave you is from Howell. It's just pretty slick. What we'll see here on the front is this is for one-tailed tests. Here's for two-tailed tests. What I'm going to do is I'm going to go through and I'm going to say I have a little significant. I'm looking at a two-tailed test. I have alpha equal 0.05 from a two-tailed test. How many degrees of freedom am I looking for in the left-hand column here, and then go through, and this is going to identify for me what my critical value is for claiming statistical significance. So, CJ, do you have your table with you?
Yeah.
Okay, tell me, if I have 19 degrees of freedom, tell me what my critical value is at alpha equal 0.05 for a two-tailed test.
2.093.
2.093, okay. Chris C, what if I have degrees of freedom 30 with, and I'm looking at a two-tailed test, alpha 0.01?
You got 2.750.
2.750, okay. So in terms of finding individual probabilities, as compared to our unit normal table, there's a lot more stuff on here. T-distribution is hard because every one of these degrees of freedom running down the left hand of the column, this represents a different curve. The shape of this curve looks different for every single one of these, going from 1 to infinity, right? And so basically with the way these are tabled, we're just saying, okay, given a degree of freedom, what's the critical value that you would need for this, right? And so if I had 2 people in my sample and I wanted to do a means-based test, right, with 2 people in my sample and a single sample Z test, I need to have a t-statistic of 12.706 in order to claim statistical significance. I don't know. I would give any of you can publish a study with 2 people in it and run a statistical test on it, I'll give you $100. That like, my test statistic is 13 and my critical value is 12.7. Therefore, with my sample of 2, I'm claiming statistical significance, right? So people see the t-table, how we're going through and using all this stuff. Okay, cool. All right. So if we're kind of tying this all together here, our Z statistic, we can use this when we have, when we're likely, or we're trying to determine whether this random sample mean that we've got is likely to have occurred in a population with a known mean and variance, okay? If we reject the null hypotheses, we're saying that based on these data, it's unlikely that the data that we've collected comes from a population having a mean and variance of some sort of a specific parameters, right? When we get into our single sample t-test, this is where we're comparing a sample mean to a known population value when our sampling, or excuse me, when our variance, we don't know it. This is 99.9% of the stuff that we're doing here, okay? Our t-distribution and corresponding degrees of freedom are going to correct for the inflation that we get by substituting our sample variance in for our population variance. As our degrees of freedom decreases, our samples get smaller, it starts to give us a larger threshold for significance. Our critical values get larger and larger, and we can go through and see that on this t-table here. Again, if we go down through Silo, if you look at for the level of significance for the two-tailed test, right, and you're looking at that 0.05 column, what's happening in my critical value as I move down that column is my degrees of freedom are getting bigger and bigger.
Your level of significance goes down.
And so we want to be careful with our term, not our level of significance, just our benchmark for claiming our critical value, right? So our critical value is getting smaller and smaller. So you see that if I want to go through and I have, let's say, a sample of, so I have 15 degrees of freedom, my critical value is 2.131. But if I have 100 people, it's 1.98. It's sort of reducing my threshold for claiming statistical significance as my samples get larger and larger. Okay. Comfortable with all of this? Okay. So factors influencing our t-statistic, the difference between our observed mean and our population mean, our reference point, our sampling variance. Our sample variance increases, so that's going to go through and make my standard error larger, which is going to drop my t sample size. Though this is the main thing. This is the thing that we most have, that we have the greatest amount of impact on to then sort of give our tests more power. I can do, and so we have different designs, so they're extreme group comparisons, right? If I'm, say, Chris, I'm looking at someone like, not just eating pathology, but someone with severe eating pathology versus a hypernormal population, a group of people who have absolutely no history of psychopathology at all. I've gotten two extreme groups. That's going to increase this difference, which is going to make it easier to find find a statistically significant effect. But then we start to wonder if that's actually representative, but I'm cherry picking from sort of the two extreme ends, right? Sample variance, we can reduce our sample variance by just having good measures, having tight measures that are not all over the place. But really what we can do, that's going to impact some. We should be doing that, but really it's going to be our sample size that's driving the power of our tests for the most part. All right, so talking about degrees of freedom. Degrees of freedom is this thing that comes up all over the place, but sometimes we have a hard time thinking about what exactly degrees of freedom is, what it means, and how we use it. Talking about degrees of freedom, we're referring to how many values, when we're calculating statistics, how many values are free to vary? How many values can be whatever they want, right? And this starts to become important in thinking about sort of how much sort of freedom we have in the calculation of our actual observations. So let's say that this is true. X plus Y plus Z is equal to 24. Okay. Nick, what's X here? What's X?
Variable.
Yeah. What's the number?
Oh, 8.
8. All right. Chrissy, what's Y?
10.
10. All right. If this is all equal to 24, Nick had all the freedom in the world here. Chris had all the freedom in the world here. Tomorrow, do you have any freedom here? No.
No, what?
Well, if this is 8 and this is 10, it makes 18, and we know that Z is equal to 24.
Oh,
Do you have
you're
any-
choosing a number? No.
Yeah, no, you
I
don't
thought
have
you
any,
meant if there was
right?
a number.
What is this?
6.
6. There we go, right? So we ran out of degrees of freedom. We would say in this equation, you have 2 degrees of freedom. First thing can be whatever you want it to be. Second thing could be whatever you want it to be. By the time we hit the third, if we've locked in those first 2, that last one is no, you no longer have any more degrees of freedom. And so in statistics, when we're talking about our single sample t-test, our degrees of freedom for our single sample t-test is the number of people in our sample minus 1. And we lose a degree of freedom because we're using the sample mean to calculate our variance, right? So if you remember when we're calculating our variance, we're going through, and here's X, right? And then we have to take our observation minus our mean and square that, right? So I can go through, have all my numbers here, right? And then have all my squared values, or excuse me, not squaring. X minus 1 here, right? And if I square all my deviation scores, what is my value going to be done here?
Something positive.
What's up?
Something positive.
Oh, I'm not
no,
squaring it. What does it have to be? Some of these are going to be positive, some are going to be negative. What's the sum of my square? What's the sum of my deviation scores mathematically? It has to be 0, right? So if we're thinking about, because we calculate our sample variance based on my mean, right? And so this observation could be anything it wants. This one, anything it wants, anything it wants, anything it wants, until we get down to the very last observation. And then it's fixed. It's no longer free to vary because we know mathematically that the sum of our deviation scores has to equal 0, right? And so by the time we have all the degrees of freedom in the world until we get to the very last one, and then whatever that is has to make that score equal to be 0. And so what we would say is the final value in this distribution is fixed. It's not free to vary, right? Statistically, it has to be, it's predetermined based on the values that have come before it. Because we're only estimating one variance within our single sample t statistic, then mathematically we would say that our test statistic, at least our single sample t, has n minus 1 degrees of freedom. This is an abstract thing that sort of really doesn't play too much into your calculation of your means-based test, but as you start to get into SEMs and sort of higher order stuff, those degrees of freedom start to sort of have a little more meaning, things like that. So just wanting you to have an understanding of sort of what's going on with this. All right, so example. So we have, once again, we're back at the local library. We're claiming that books on average 20 years old. To test this claim, the student randomly selects 30 books and records a publication date for each. Sample has an average age of 23.8 years. Sample variance was 67.5. So this is going to look similar to stuff that you're doing right now. So in a sense, state the null hypothesis being tested. Christy, can you give me the null?
Okay, so there is no difference, or what, let me rephrase this. All right. The books in the sample will be 20 years old.
Mm-hmm. Almost perfect. Where did Chris get sidetracked on this? Okay, so yeah. What are our hypotheses tests about the sample? No. CJ, what are we looking at with our statement of our hypotheses? Population, right? So what I would say, in a sentence, state the null hypotheses being tested, I would say the appropriate, or the statement of the null hypotheses would be population of books in the library has an average age of 20 years. Okay. So again, remember that I don't need to put together I don't need a statistical test to tell me whether or not the sample of the average age of my sample of books is equal to 20. I just look at it. If it's not 20, then I'm like, okay, then it's not 20, right? But I don't care about the sample. What I care about is the population of books, right? And so my hypothesis is technical statement, or correct statement of my hypothesis would be that the population of books in this library has an average age of 20, right? And then we would use sort of statistical notation to indicate null and alternative hypotheses. What we're going to do here, jump to calculating the 95% confidence interval, the point estimate of our books, okay? So I've got 30 books, average age 23.8, and what do we got? I say variance, oops. Variance is 67.5. What do I need to do first to calculate my confidence interval? Calculate my standard error. So my standard error is going to be, someone get their calculators out. We're going to take the square root of 67.5 over 30. Someone tell me what my standard error is here. What is it? 1.5? Is that what other people got? Chris, did you get that? Okay, cool. Yeah, I think this works out a whole number or even numbers, so that's good. All right, so I've got my standard error. That's good. What else do I need to calculate my confidence interval here? Okay, you need a z, right? But are we working with a z distribution or not? So what do we need? We need our t, our critical t, right? So here, what are our degrees of freedom for our single sample test? 29, right? So my degrees of freedom equals 29. Alicia, can you tell me what my t critical is for alpha equal 0.05 and 29 degrees of freedom? Yeah, 0.05. Two-tailed test, 0.05. What's my critical value? 2.045. 2.045. Is that what other people got? Okay, cool. So we know that our confidence interval is going to be our point estimate, 23.8, plus or minus critical value 2.045 times, someone's going to turn this around. Calculate your confidence interval first before you calculate your test statistic, because otherwise what someone will do is you calculate your t-test and then plug your t-test into that, and that's wrong. You don't want to do that. This is going to be your critical value, right? So what are my markers? What are my benchmarks? Okay. And so if I calculate this out, what's my lower limit on this? What did you get on the lower limit side?
20.73.
On the 20.73? Nope, not gonna be negative. So, Chris, or CJ, what did you get? Did you get 20.73?
Yep.
And then what's the upper limit?
26 point.
What is it?
26.86.
26.87.
87.
Okay, cool. Do these figures match up with what people got? Okay, cool. So, Chris M. So give me an interpretation of that interval estimate there.
So we could say with 95% confidence
Okay,
that.
we could, let's not say that though. So with 95% confidence starts to get into problems with sort of misinterpretation of these intervals, right? So if we go into it knowing that we've got a 95% confidence interval, how would I interpret sort of the bounds here?
They don't really appear to be that large.
Okay, so this is good, right? So we've got about
The upper and lower bounds.
the upper and lower bound is about 7 years, right? So, I mean, and this is, years are a nice unit because they kind of mean something, right? And so we can say, well, is a 7-year span, is that a lot or a little? I don't know, I guess it's debatable depending on what if we're talking about age of books, it sounds pretty big, right? But that's probably because our sample's pretty small, right? What else, Alicia? So what else could we infer from sort of our confidence bounds here?
Isn't it 95% of the intervals, within 95% of the intervals being would fall within that range?
And so again, this is, you're absolutely right in terms of the technical definition of a confidence interval. The 95% piece is about the process, right? So if we were to conduct this study, if we were to randomly sample 30 books from this library, and we were to calculate a confidence interval from all possible samples of 30 books that could be drawn from this library, and were to calculate confidence intervals for each one of those estimates, 95% of those intervals would actually contain the true population parameter, or the true average age of the books in the library, right? But do we know for this individual one whether that's contains it? And can I say that there's a 95% chance that this interval contains 0? Why not? Because I don't know. Because either the true mean of the age of the books is either in there or it's not, right? It's not like sometimes it will be or sometimes it's like not 95% of the time the population parameter is not going to fall between 20.73 and 26.87. It's either it's in or it's out, right? And so this is where I want you all to, and you get good at this, it'll be second nature because we're going to be doing it a lot. But one, I think, remember we can talk about and interpret our interval estimates as, so based on the data that we've collected, we would expect, we would see, so our best guess for the population, mean age of books in the population of library books here is going to be 23.8. But any guess or any estimate ranging from 20.73 to 26.87 years would be compatible with the data that we've collected. Right? Those would be reasonable estimates. Those would be plausible estimates. So our best guess is about 23.8 years, but We also have a lower limit of 20.7, which would be plausible based on the data, or an upper end of 26.8 or 26.9 is reasonable based on our data, right? Because we know that this isn't the actual true population value. We're hoping it's close. It's our best guess. But with the data that we've collected, assuming that our methods are good, anything ranging from about 20.7 to 26.9 is going to be reasonable, okay? So if CJ says the mean age of population, or the mean age of all books in the library is 23.8, and Chris, you say that's dumb, I think it's 22 years. I would say, well, you're both right. Based on the data we've got, CJ's guess is probably a better guess, but yours is equally, yours is reasonable too. I can't say, based on the data that we've collected, that that's a bad estimate, right? And even values falling outside this, if I said the actual population estimate, or the actual population value is 20, is that impossible? It's not impossible. It's not likely given the data. We would say that an estimate of 20 is not compatible with the data that we've collected, but it's certainly possible, right? Because for this interval, I don't know if this is one of the 95% of all possible intervals that could be calculated that captures it or not. All I can do is work with the data that I have and say, well, 20, you can make 20 as a guess. It just doesn't appear to be compatible with the data that we've collected here. Yeah?
How does sample size relative to the population size? Back to, so like,
That's a
if
good
this,
question, yeah.
If this library is like huge, you only took 30 books,
Mm-hmm.
how does that factor, what do you do to factor that in?
That's a good question. If it's a small library, if it's, so I don't know, my high school, or my elementary school and high school, the town pavilion, it's got like sample of, or it's had 100 people in it, like I had a graduating class of 25, right? So the pavilion library, who are you smirking back there? Right? So very, very small sort of rural community, right? And so our library maybe had like 200 books in it or something like that, right? From that standpoint, then this would probably start to be, it would screw with this, right? Because this is assuming sort of basically a very, very large population, and so, but 30 as a percentage of infinity is really small. 30 as a percentage of 20 is quite big, and so this, I would start to probably adjust my interpretations of this quite a bit. But usually that's not sort of the situation that we're in, because a lot of times what we're doing is we're talking about hypothetical populations, right? Or if my library only has 200 books, probably don't have to worry about statistics. I'm just like, well, let's just look at the data, all the books, and just report that. It would take a little bit of time, but at least we'll know, and then we don't have to worry about statistics because we actually have the population parameters. But that's a very good point, right? In terms of this is based on assuming that the population is massive or unknown or unknowable. But absolutely, as we start to get, our samples start to get a bigger proportion of population, they start to get good. Now, normally, that's just a direct function of the sample size. We don't worry about the size of the population so much, but that's a good consideration. Other questions on the confidence interval here? Okay. Conduct a hypotheses test at alpha 0.05, right? So we've got most of our work done here. So we got T is going to be equal to 23.8 minus my value under my null is going to be 20 over my standard error 1.50 gives me a T statistic of what? 2.53. Is that what we got? Okay. And so from a classic hypothesis test to hypothesis testing situation, this is my test statistic. What's, Chrissy, what's my critical value?
It was 2.045.
2.045. So just based on my critical value and so my test statistic, do I reject or fail to reject a null? Reject a null, right? Again, if I'm going through and I'm saying, here's my distribution, here's my critical value is 2.045, my test value is here at 2.53. That's in the critical region there. And based on a classic up or down test, I would say I would reject the null hypotheses at alpha equal 0.05. Okay. Now, what we would probably want to, what we would want to do now is calculate actual p-value for this, which can we calculate a p-value based on for this test statistic based on my t-distribution, my t-table that we got here? No, right? Because I would have to say, so I've got 19 degrees of freedom. My actual test statistic doesn't fall on any of those, right? So I can't actually calculate that. But the power of technology, p-value calculator again, like this graph pad. So I can go, so my test statistic is, so tell me my test 2 point.
Oh wait, that's your.
Yeah, my test statistic is, what is it? 2.53. 2.53, and my degrees of freedom, 19. 29, thank you. 29 degrees of freedom. Compute. Okay, so my p-value here is 0.017. So this is a nice, again, would encourage you all to bookmark this site. It's just nice to have up there. Okay. And then sort of wanting to go through and summarize our conclusions. So what I've done here is just kind of write this all out just so that you have it as an example. So we've got statement of our null hypotheses, right? Again, notice that we're talking about this in terms of population. And so when you're stating the null hypotheses, I do want you to focus on sort of one, sort of identifying the population. And again, we don't think about this enough, right? We just collect our samples of convenience and don't think about populations to which we're hoping to generalize to. I think this is just a nice exercise to state that we are, in fact, thinking about populations and then sort of talking about the units in terms of what we're actually looking at here, right? So we've got mean age of population books contained in the local libraries, 20 years. Our statistical notation, our confidence intervals don't appear to be on base. Did we get off somewhere?
It's a different end.
What's that?
Your end for this sample was 20, our end was 30.
Oh. Okay, whoops, yeah. Laura, can you tell me to fix this? Okay. Yeah, 20 years, not 20 books. Okay. But there we go. Okay. T-critical, this is our test statistic. This is a p-value. And so I guess if we're going from 30 books to 20 books, then we are sort of shifting this down a bit. But if we had sort of gotten this, this might be sort of how I might go through and start to knit all this stuff together to start talking about interpretations, right? So I don't want to read you things that you can read yourself, but sort of saying average books sampled in this study, so identifying sort of the sample size was 23.8 years, with population estimates ranging from 20 to 27, identified as compatible with these data, right? So I'm going through and giving it a practical interpretation of the confidence bound, right? I'm saying we found 23.8 years, but basically our population estimates ranging from, so there was some rounding here, right? I would still say 21 to 27 years compatible with the data. Important to note, precision of these estimates, so your margin of error, that's just your critical value times your standard error, so your plus or minus, right? Margin of error, 3.8 years, the range of the interval, sort of the two, limited by the number of books in the sample, while the upper limit of the interval supports estimates that exceed librarians' guess by more than 7.5 years. Estimates at or near 20 years remain plausible given current data. As a consequence, results are generally inconclusive regarding the extent to which books in this library are close to the expected range of 20 years. thinking about how to go through, so what we would do from a classical standpoint is just say, it's significantly different than 20 years or something like that, right? But that doesn't give us a lot of information. It just means that the exact age of the book in the library is probably not 20 years. But if we go through and we take a look, in this example, 20 people, I'm just like right under it, right? I mean, so I could say it's just barely catching it. So my upper end said if I said there's average age of the books in the library of 27 years, that's a reasonable guess based on the data that I've collected. It's not the best guess. 23.8 is the best guess. But you try to use this interval estimate to go through and talk about sort of upper and lower limits. And so then trying to draw some basic conclusions about things. So here we're saying our p-value is 0.052, so we're just a little bit under. Here our p-value 0.017, but I would still say, so we have so a lower bound of 20.73, upper bound of 26.9. It kind of depends on like how much of a difference. So let's say that the average age of the book is actually, the average age of the population of the books actually is 20.7. Is that a meaningful difference? 0.7 years, like, yeah. So, I mean, I could claim statistical significance, but I could also say, I mean, it looks like maybe it's different. There's, I guess, some evidence that it's a little bit different, but I don't know. But just my sort of yes or no dichotomous decision on statistically significant doesn't tell me by how much, right? Is it sort of a meaningful difference? At the low end, it seems like it's a kind of a trivial difference. At the high end, kind of a substantial difference. It's just we have a really wide interval here, and so I'm not sure. We can't make a lot of strong claims based on these data. And so again, I'm trying hard to go through. It's not easy for me to be like, oh, you guys need to sort of do this. So as we're going through, trying to put together these, at least sort of a way I might go through and interpret this. And as you're going through writing up your own stuff, go through, take a look at this, and again, you can use this as kind of a model. Please don't use it as like a cut and paste template, but also sort of I haven't copyrighted this these texts, right? So that it's not the sole propriety of me, right? I just am trying to think about like ways that we can talk about things that don't necessarily just break it down into sort of statistically significant. Questions on what we've done here? Let me look at that. All right, we'll finish up. We'll talk about effect sizes and then jump into, we'll then take a break. So this is classically what we go through, and this is our classic hypothesis testing. Looking at critical values, saying, have we exceeded the critical value, talking about statistical significance. But the problem is our classic hypothesis tests don't give us any indication of the magnitude of an effect, right? Again, if I have 100,000 people in my sample, everything's going to be statistically significant, right? What would be nice if we had some way of calculating or estimating sort of the magnitude of an effect in our population, okay? And this is where effect size comes in. Again, effect size, thinking about this in terms of the absolute magnitude of an effect, but remember that this, any statistically we calculate from our sample, this is just an estimate of the population value, right? In sort of somewhere out in the ether, there is a real sort of effect or sort of a real estimate of the population difference between men and women on agreeableness, let's say, right? Somewhere, depending on the population, that is something out there, right? And we can say, are those two things equal? And no, they won't be exactly equal. And so what we could ask is, how big is that difference? What's the magnitude of that effect? And what we can do is we can, based on our sample data, we can calculate an effect size to try and get an estimate of population value for the magnitude of that effect. Now the tricky thing with effect sizes, have people worked with effect sizes? Have they incorporated those in their research? Have done that? Like show of hand, let me see. Okay, so some, but not always. the thing that about effect sizes that people have been talking about effect sizes for years, and these are very, very important in terms of building up our inference. The problem is that depending on what statistic or what analyses that we're using, there are different metrics of effect, right? So if I'm doing a mean-based comparison, things along those lines, right? But if I'm doing a regression, we have a whole different set of effect sizes, several different ones, right? And they don't necessarily all translate with one another. And then if we're doing ANOVA stuff, then we've got a whole different set of effect sizes. And so one of the nice things about P is the same thing across any test that you're doing. Effect sizes, you have to sort of understand about different ways you can go through and calculate it. And there, as we go through, a big part of effect sizes is deciding which one of these options do I choose. I've got like 3 or 4 different ways I can go through and calculate effect. Which one makes the most sense, and what are the strengths and weaknesses of each one of these? Then how do I interpret it? How does this relate to another study that used a different analysis? It starts to become more complicated. Also, SPSS doesn't spit out effect sizes for you, which makes then people don't calculate them because then they think that's a headache, right? So there's a whole sort of big sort of issue around. So there's reasons why people don't use these as often as they should, but these should be included, again, in sort of that Wilkinson paper. With every sort of primary analysis should have some measure of effect, right? But then you get into some of the stuff like Ben was talking about today, where he's doing sort of intensive ecological momentary assessment, sort of experience sampling stuff, where there are no effect sizes. I mean, there are effect sizes, but none of them are much any good, right? And then he's up against editors saying, oh, you have to calculate an effect size. It's like, it's not one that's been developed, right? And so it's just a much, things are much more in flux within this. But luckily for us, for means-based stuff, it's less of a Wild West issue, okay? But again, at the end of the day, what this does is it helps us augment our interpretations, right? So we can say, yeah, some value is likely not 0, but by how much? Now for our single sample T, we can just go through and calculate raw difference as a simple measure of effect size, right? So for this library, years mean something, right? I understand, we all have an understanding, hopefully, of what year is, right? And what constitutes a lot of year difference or not a lot of year difference, right? So we could, for this example, we could calculate an effect size by just taking 23.8, subtracting it from 20, a 3.8 difference. So the difference in the magnitude of the difference relative to the my reference estimate is about 3.8 years. Okay, I know how far off that is, right? Or if I'm working with income, right? If I say the difference between men and women in the same careers in terms of pay is $5,000 a year difference, right? Or I can say I found a significant difference, it's $500 a year difference, right? Those raw differences mean something to me. I identify this as a problem, or this is a big difference and this is a small difference, right? So just the raw difference can be a meaningful sort of measure of effect. Or if we're working with, Nick, if you're talking about number of drinks, rather for a normative student versus a number of alcoholic drinks a month, right? Just the raw difference between sort of this group and that group makes some difference, right? Or Chris, if you're talking about eating disorder or eating pathology, and you're talking about difference in terms of pounds and weight, I know what that is, that's meaningful, right? And so this can be a very, very effective way of expressing an effect size if we have meaningful units. But a lot of times we're not using things that have intrinsic meaning, right? We're using the PTSD checklist or the Beck depression inventory or a relationship satisfaction measure or something like that where the units aren't meaningful, right? And so what we would do then is we can go back through and then calculate difference in terms of standard deviation units. And this starts to go through and have more meaning. So what I could do is I could go through in this example and I could take and calculate a Cohen's D for this, where I would take D is 23.8 minus 20 over, what's the square of 67.5? What is it? 8.2. And so what's 3.8 divided by 8.2? So what I could do is I could say, for this difference, I say here, with 30 participants, we did find a significant, we could claim statistical significance if we wanted to phrase things that way, right? But that just means that sort of this value, based on our estimate, that this value is reliably different than 20, right? But by how much? Here we could go through and we could calculate our test statistic, and all we're doing is we're interpreting this as a unit of difference in terms of standard, or difference in terms of standard deviation units. Okay, so I would say there's just under a half a standard deviation. Sort of books in our sample are about a half standard deviation above what was expected based on the sort of point estimate under 20 or the value under the null, right? All the stuff that you guys have been doing in terms of calculating these Z-statistics and interpreting Z-statistics, a lot of this is so to get you comfortable with interpreting things in terms of standard deviation units. Is a half standard deviation big? No. It's what we go through and we would classify this as a medium effect, okay? Now these are benchmarks for interpreting D based on some classic work by Cohen. And Cohen, when he was putting out these benchmarks, said, do not use these as a universal benchmark for everything. But if you're just kind of wanting to get a general idea of what's kind of big or small, here's some benchmarks. And so what we did immediately is that everybody uses them, I guess they're sort of rock solid infill. So anything, if it's 0.49, then it's a small effect size, right? So that's nonsense. So again, these are benchmarks. Do not use these sort of rigidly, but if we're looking at an effect size of 0.2, and what Cohen did, Nysen did when he was laying these out, is trying to give these in terms of something that's meaningful. An effect size of 0.2 suggests about 2/10 of a standard deviation, right? So this is pretty small. Cohen identified this as the difference in height between 15 and 16-year-old girls, right? If we think of if we had a bunch of 15-year-old women and 16-year-old women and looked at their heights, statistically, the 16-year-old girls would be taller than the 15-year-old girls, but it probably wouldn't be something perceptible that we could see. We probably couldn't just eyeball and see the difference there, right? A medium effect, around a half a standard deviation. Cohen gives an example of this is the difference between heights of 14 and 18-year-old girls. Here, we've got young women who probably are sort of just about or just starting into puberty, and so young women who are sort of emerging adults. Here we're going to see clear differences in height between these two groups of women. It's going to be obvious, or so it's something that we can detect just by looking. A large effect, D equals 0.8, difference in heights between 13 and 18-year-old women, so it's women, young women who get to hit puberty, and sort of women who have, and sort of young adults. It's going to be very clear and obvious and large differences between those two groups. So again, this is when Cohen was putting this out, trying to give people an idea of kind of like how big these were looking at. But again, one of the things I'm going to have you read is a paper called When Small Effects Are Meaningful and Important, or something like that. I can't remember exactly what the paper is. And so this isn't sort of this is not indicating importance, right? Your assessment of whether or not things are important or not is based on your understanding of the field, understanding of the design, what's being measured, and all that, and all those types of things. But these are kind of conventional standard benchmarks that roughly use to gauge kind of where things are at, okay? But at the end of the day, interpreting our Cohen's D in terms of units of standard deviation, right? Then, talking about possible conversion, one of the things that's at the heart of meta-analyses is taking effects from different literatures having used different statistical methods and trying to go through and estimate effect sizes based on a common metric. It's often an R coefficient in terms of measuring magnitude of effect. So we can go back and forth and sort of calculate statistics from other statistics. For the things we're doing, do this, right? If you have means and standard deviations, do this. Like, this is what you need to do. But if Chris writes a paper and he didn't give me effect sizes, I'm like, Chris, right? But you gave me t values, right? What I can do is there's a mathematical relationship between t and d. if you give me your test statistic and your number of people in the sample, I can go through and estimate a t-statistic based on the test statistic there. This is super handy because probably when you're trying to run your power analyses for your thesis or dissertation, people aren't going to provide means and standard deviations, which drives me nuts. And probably didn't provide effect sizes, which also drives me nuts, but they might give them a t-statistic, and you go back translate that into an effect size to go through and calculate from there. All right, questions about effect sizes? Yes?
I think when you first mentioned the units of standard deviation thing, so
Yeah.
are we saying that the difference between the two groups is about half a standard deviation?
This is a little bit tricky with the single sample test. We would say that books in this sample are about a half standard deviation above the age expected based on the null, right? Because we don't really have a group, we just have sort of an actual point estimate, a reference value, right? So we're not talking really about differences because this group is from the group that I'm comparing against, right? And we'll get into our independent sample, then we'll say, you know, college freshmen are X standard deviations of X below sort of seniors or something like that. Here we're just talking about units of standard deviation difference from whatever our reference value is. Other questions? Okay, cool. Let's take a quick break. Yeah.
As unrelated, but Dr. Estes was wondering, for GenSci, we're using
People feeling comfortable about general interpretation, calculation, and effect size. And we're going to go through examples on how to go through, calculate, interpret, and things like that. Oh, we got George Washington. Today's, again, talk about, so Wilkinson saying that, again, we should be providing effect sizes, interpreting effect sizes in the context of our research, previous effects, things along these lines. Again, we're increasingly getting to a spot where over the course of your career, just reporting whether or not something is statistically significant or not, p less than or equal to 0.05 is not going to cut the mustard. So we wanted to go through and practice thinking about effect size in terms of magnitude and things along these lines. Okay. So now we're getting in the weeds. This is brand new stuff, okay, have incorporated in. Again, remember that primary criticisms, or one of the primary criticisms of null hypotheses testing is that it's not doing the things that we as researchers in a sort of classical sense, and again, applied researchers like we psychologists, it's not doing the stuff that we think it's doing. And so what ends up happening is we end up over-interpreting things and putting far more weight into them than we probably should, right? So if we're talking about p-values, I'm having you go through and read a number of different papers. Who here is sort of kind of keeping up on their readings? Ish? Okay, it's fine. I do everything at the last minute too. It's a hard habit to break. It's not great to try and keep up on it, but you'll notice if you're going through and reading these papers, who's feeling like they're reading a lot of the same thing over and over and over again? It's intentional, because this is hard things to get, but the more you read it and the more you start to become familiar with these ideas, right? A lot of these papers are talking about how not to interpret p-values, but one of the nice things about this 2019 paper, I've drawn a lot of stuff, they start to talk about ways that we can interpret. What can we, what types of interpretations can we make based on p? And compelling arguments for interpreting our p-values as an index of the extent to which data that we've got are compatible with the null given the assumptions of our underlying model, right? So if I've got a p-value of 0.05, I'm saying, okay, so these data sort of are sort of not super compatible with the null. But if I have a p equal to 0.00000001, those data are really not compatible with the null model or the null hypothesis in the underlying model, right? And so we can use that. As that p-value gets smaller and smaller and smaller, it's telling us that these data are increasingly unlikely given the null model that's been specified, right? But we've got a problem in terms of the scaling. It's not a linear scale. And so the difference between p-value 0.01 and 0.10, that's a lot different. So that's suggesting a much greater degree of incompatibility than the difference between 0.9 and 0.99. 0.9 and 0.99 are sort of right here and right here. 0.01 and 0.1 are these far apart, even though the actual value is sort of the same across these. Same type of thing. If I have, for those of you who take Tara's assessment course, right? If I have the difference between, to go from IQ score of 100 to 105, that's sort of a trivial jump. If I go to 130 to 135, that's a much larger jump. Same type of thing with these p distributions, okay? We also have concerns that this bright line interpretation, p less than or equal to 0.05, results in overinterpretation of things, right? Again, we talked about sort of not using the same standard. If it's less than 0.05, we say, well, we don't know if we're doing our job correct, right? If we're not doing our job correct, we say there's no difference. That's absolutely wrong. But if it's less than 0.05, we say, oh, well, the data are inconclusive, we don't really know. But as soon as it tips over to 0.05, we say this is a real effect. And we expect it to replicate, and we get upset when it doesn't, right? And so what happens when we just identify things as statistically significant or not, it infers things about replicability, meaningfulness, and things along these lines, right? For example, some of the stuff in Ben's talk today, right? He was presenting some effects that were sort of modest p-values and things like that, right? But what he was talking about is not having a whole lot of confidence, but then going through, and if we're getting the same thing, we're replicating the same thing again and again and again, now I can start to have sort of more confidence in this. But for a single test, for a single study where I've demonstrated an effect that no one's ever talked about, if I've got a p of around 0.05-ish, I should be really hesitant to put too much into that and sort of think that this is something, or infer much in terms of replicability. And so one of the things that's been proposed, right, in this 2019 article, ASA is just kind of throwing things out there. These are things that people have come up with as something to go through and maybe as adjuncts to null hypothesis testing or replace null hypothesis testing. It waits to be seen to the extent which some of this stuff catches on, and sometimes we come up with something and people are excited about it, and then there's a fatal flaw that we don't know about until someone brings it up, and I go, whoops, that wasn't an exciting thing, or that's maybe not the best thing to do. What I've done here is taken some recommendations that are easily sort of derived from the stuff that we're already doing, and adding these on as adjuncts to help with inference and sort of think carefully about what stuff is going, what our statistics are telling us. And then, if you get out of this class and you want to use these, that's cool. If 3 years down the road someone comes out and says S value is stupid because of this reason, then you're like, sweet, I don't have to do that anymore, right? So it's things that you can add or sort of, it's based on stuff that we're already getting, okay? But these Shannon information values, or S values, offered as an alternative way to interpret sort of our P and think about strength of evidence against our null hypotheses, because this is really where it comes down to, right? We're not thinking about, oh, the null is not true or it is true. Thinking about how much evidence do our data give us against the null hypotheses, and thinking about this in terms of a continuum. So an S value, we can calculate this as a nonlinear transform of P. Greenland gives S as the negative log base 2 of P. That's actually difficult to get out of your calculator unless you transform everything to base 2 units. But with some basic algebra, if you remember anything about your logs, which I don't expect anybody to, but if we take the absolute value of the natural log of your p-value over the natural log of base 2, this will give you your S value, okay? And so what we do is we can go through, calculate our S value, and then round that score to the nearest whole integer, okay? And so what we interpret this S value, so it's basically a transform of your p-value, it changes the scaling issue, right? And we would say that this, so based on the S value, we would say test provides roughly the same evidence against the null, given our model A as observing S successive heads in the tosses of a fair coin. So if I have, and just for example, if I take I take, whoops, p-value, 0.05, okay? My S value in the absolute value, my natural log of p over the natural. So if I take 0.05, I take the natural log of that, it's going to give me negative 2.9957 over the natural log of 2.695. I'm just carrying these out so you guys can see this, right? And then if I divide those two, it's going to give me the absolute value. It's going to give me the absolute value of negative 4.32. Okay, and then we're just going to give that as equal to 4. Okay. So what we've done is just run through the transform of that p-value. And you may have to go through, depending on your calculator. This is why I want you to have a scientific calculator to be able to go through and calculate logs and sort of other fancy stuff like that. But essentially what this is doing is our p-value of 0.05 gives us an S value of 4. Okay? And what we would say, if I find a study and I find an effect that has a p-value or a p-value of 0.05, this gives me an S value of 4, suggesting that this test gives us about the same amount of information against the null hypotheses as, given the underlying model, as 4 consecutive heads would give us against sort of the hypotheses that I'm working with, a fair coin. Okay. Now, if I flip a coin tomorrow, I give you the coin, I have you flip it, right? And it's heads. You say call it, I say tails, and you get heads, and it's heads, and it's heads, 4 times in a row. How convinced am I, or should I be, that you actually have a fair coin or a coin that's sort of not, sort of off? I'd be skeptical, but would I be willing to probably, well, you don't know me, I'm a degenerate gambler, right? So I probably wouldn't be willing to stake a whole lot of money on the fact that that was actually not a fair coin, right? It's suggesting, it's not common, it's not likely, but at 0.05, it's not a ton of evidence against the null hypotheses, right? And so this is the idea behind these S values, is thinking, sort of using this as a way to start to gauge the strength of evidence against the null given the model that we're using. Does that make some sense? You can kind of see how this is, how we're using this. Remember, this guy is super excited, like, yeah, overexcited. If we actually go through and we take a look at, for different p-values, so this is a situation where we've got t with 50 degrees of freedom. So we got, sort of, for means-based tests, that's some degrees of freedom, right? But we've got our test statistic here and corresponding p-values, our natural log base 2 of p, and then the S that we get out of this. So if we see 0.05, right, gives us an S value of 4, right? The evidence against the null hypotheses, given our underlying model, would be about the same as 4 straight heads in so what I'm telling you is a fair coin, right? We also see that 0.05 has the same S value as 0.08, right? And so starting to see that these, in terms of strength of evidence, are not terribly different, right? This will get you published. That won't, right? But sort of from a statistical standpoint, for building our inferences, wanting to think about like sort of what this actually means, right? Because what we do is we say, oh, this is the line that we decided, and so anything that ekes across this is a real thing. And I'm very, very confident that this is a real thing, when actually we should be sort of much more guarded in terms of sort of our extent to which we think things are going to go through and be statistically significant, right? But as we start to go up, 0.01, 0.05, 0.00 1, right? And so this starts to get into sort of some of our reporting, I think, which we'll play around with this semester. So we go through and talk about providing exact p-values. This no good. No one do that. If anybody does that, you're gonna lose points, because it's just, basically you're saying that anything sort of beyond here is identical, right? Not reasonable, okay? But if we look at, we tend to report p-values to 3 decimal places, right, just in terms of convention. And then after that, we say p less than 0.001. But as we'll see in some of these examples, so p equal 0.001 associated with an S value of 10, right? If I go p 0.0001, that's the difference between 10 straight heads and 17 straight heads is pretty big, right? And so if we're thinking about reporting p and interpreting p as a continuous measure of evidence against the null, or a continuous index of the extent to which our data are incompatible with the null hypotheses, all of a sudden it starts to make more sense to have some way of reporting these p-values to get to how small they are, right? Because this could be something that's sort of right about this level, or it could be something that's way down here or even more extreme, right? So what I've done, again, sort of in terms of change, is starting to play around with different ways of reporting your p-value to actually communicate sort of how small this is. Now, if you're reporting to people who are familiar with test statistics, if you tell me that you have a t statistic of 13, I know what that means in my head. I'm like, Jesus, that's huge, right? But people may not intuitively know that, particularly if they don't do a lot of method stuff. But if you can say not only is p less than 0.001, it's, say p equals 2.34 times 10 to the negative 12, right? That means we add 11 zeros in front of that 0.2. That's very, very small, right? And again, if we're thinking about interpreting our p-value as, again, continuous index of continuous evidence against the null hypotheses, so this doesn't really capture what's going on with that, right? So we'll go through, do some examples, and sort of show you some ways you might go through and report this, and who knows. I'll tell you how it goes. I'll try and start publishing some of this stuff, and maybe reviewers will tell me to knock it off, start being an asshole, but I'm trying to go through and explain why we're doing some of this stuff. Okay. So questions about S values and how all this stuff comes together. Okay, cool. Other thing that I picked up that I think is an interesting way to think about things. Anybody ever done anything with Bayesian statistics? No, me neither. You a little bit?
I went to a class for it for like 2 weeks and then it was too much.
and then you just dropped out. Yeah. What is your understanding of Bayesian statistics based on the class that you were in?
What I retained was that they don't think that p equals or is less than 0.05 is a valid way of testing things.
Yeah.
So it was too abstract.
Yeah.
So I can't help right now.
The basic idea, remember that we, with our inferential statistics, so the question that we're asking with our null hypothesis testing is, assuming the null hypothesis is true, what is the probability of obtaining these data are more extreme, right? Assuming that the null is true, so how likely are these data? This isn't actually the scientific question that we want to ask, right? We don't want to say, assuming the null is true, how likely are the data? The question we'd like to ask is, given the data, how likely is the null hypothesis to be true? But these aren't interchangeable probabilities, right? And so the argument against null hypothesis testing is you're not answering the question that you want to answer. And so what we do want to do is we want to use our p-value to answer what Benjamin and Berger are calling the strength of evidence question. How strongly does the evidence from the data favor our alternate hypotheses relative to the null hypotheses? But our significance test, our p-value, only provides a test of the null, right? Our null is the only thing being tested, and it's just saying, assuming the null hypothesis is true, how likely are these data, how likely would it be to obtain these data as more extreme, right? And so then we go through in the last lecture, we went through all the problems with the logic problems and things like that that go through So one of the alternatives, so the way to do this, and this is where Bayesians come in, they say, well, let's just answer the damn question we're interested in asking, right? And we can do that using some Bayesian statistic calculation of base factor. And base factor is what we do is we take a look at the average likelihood of the data under the null, or under the alternate hypotheses, over the likelihood of the data under the null, okay? So basically we've got essentially an odds ratio, right? What's the likelihood of the data under the alternative versus the likelihood of the data under the null? But the problem is, and this is where when you hear about things sort of orbiting, talking about Bayesian statistics, the key weakness of Bayesian approaches is it requires the estimation of a prior probability. It means before I collect the data, I have to have some estimate of the likelihood of these data in the population, right? And this is really, really hard because depending on what estimate I come up with, that's going to really start to change some of my statistics. So if you remember the schizophrenia example that we went through, right? And in the last lecture, when we're looking at base rates of schizophrenia, sensitivity, specificity tests, and we have a screener with amazing specificity, amazing sensitivity. When we go through and we actually calculate the likelihood of a positive test given a non-case, it's not really small. It's actually the majority, or so it's quite large. That was all based on that prior probability. So if I'm looking for, if I have a screener for, say, school shooters or something like that, right? And my test is, are you a man, right? I'm going to have perfect sensitivity. My specificity is going to be all terrible, right? And so what we're going to be looking through with the base factors, depending on sort of what that initial probability is, starts to impact sort of the whole sort of estimation of stuff. But what Benjamin and Berger are proposing is calculating an upper limit on your base factor based on your p-value, okay? And so base factor bound. This is going to be under the best conditions. So they're identifying best conditions, assuming that the null and the alternative are equally likely. There's a 50-50 chance, right? The alternate hypothesis is equally as likely as the null hypothesis, which is being incredibly, incredibly generous, right? What you're doing here is calculating your base factor bound as 1 over negative e times your p-value times the natural log of p. And what you're going to get is a base factor. Base factor bound represents the largest possible base factor that could be consistent with the p-value that you've observed, okay? And we're interpreting this as the strongest case for your alternate hypotheses relative to your null based on the data that we've got, right? So essentially what it's doing is it's giving you an odds ratio, and it's saying under the best possible circumstances, this is the maximum, sort of the peak of sort of the strongest case for the alternate relative to the null hypothesis, okay? And so,
What does the E represent?
this is base E. So E is a mathematical constant. Do you have a scientific calculator on you? If you take if you take, well, natural log is base E, but if you take, so have an E on your calculator?
I have one on the
Okay,
computer,
yeah, so if you take, so punch in 1, and take that to, or actually clear that out. You should be able to just go hit E. Will that give that to you? Yep. Oh, no, something went wrong.
It's like to clear that, yeah.
Yep, there we go.
Oh,
Okay.
okay.
So E is equal to 2.71828.
1.82846.
E is like pi, okay? E is the base of your natural log, right? So if you take the natural log of 1, we'll natural log of 1, it'll give you E. It should, right?
It's 0.
Oh, whoops. So take 1. There we go. E to the first. Do you see that on your calculator? You got it? Do you find it? Okay, do people able to get to this constant here? Okay, so this will be important because it's a non-repeating decimal like pi that goes off into infinity, but you don't want to just round it to the first decimal because it'll start to screw things up, right? So what we're doing here with your base factor bound is going to be 1 over negative E times P times natural log of P. Okay. So if we're going through and calculating base factor bound for our different values here, so we've expanded this table. So we've got our P, we've got our S values, and this is base factor bound. And remember, our base factor bound is the odds of the strongest odds for the strongest case for our alternative relative to the null. Okay, and so odds are one of these things that we'll get into more when we get into logistic regression, things along those lines. But odds basically the occurrence of an event relative to the non-occurrence of an event, right? So if I say, we're going to give some examples of, let's say, rolling a 3 on a dice, right? You've got a 6-sided die. There's one way to get this. There's 5 ways not to get it that way. So we would have, our odds would be 1 to 5, or excuse me, 1 to 5 odds, right? Or 1 to 5 odds. Or if I said rolling something other than a 6, right? There are 5 ways to get something other than a 6. There are only 1 ways to not get a 6. So we would say 5 to 1 odds on that, right? We can take our odds and we can translate those into a probability. If we take the odds over 1 plus odds, right? That's going to give us probability, and then we can take the inverse of that and talk about the odds again. So odds are nice because we can work those sort of either way, move those back and forth, and calculate some probabilities, right? So for our p-value, let's say p.005, gives us an s-value of 8, right? That suggests that if I get a p-value of 0.005, the evidence of this test against the null hypothesis is about the same as flipping a coin 8 times, getting heads 8 times, and sort of how much evidence of that is against a fair coin, right? We could also calculate your base factor bound. It's going to be 13.89. Right? So if we take 1 over negative 2.718 to 8 times 0.005 times it's the natural log of 0.005. Negative 5 point. Negative 5.098317. Okay. That's what we're getting there in terms of our base factor. And so what we would do is we could go through and then calculate this. In addition to putting together all of our statistics, right? We could say that based on our data, the likelihood of our null hypothesis, our alternate hypotheses is at most 14 times that of our null. Again, we're sort of rounding up here, right? So we're saying that the odds of our alternate hypotheses to our null, this is 14 times more likely than our null hypothesis. This is pretty compelling, right? If this event a whole lot, that's a pretty good bet, right? We could also say if we take our odds, because this is actually, so base factor bound, so we're giving these as just a number, but essentially what this is 13.89 to 1, right? So for every one occurrence of our null, we're getting close to 14 occurrences of the alternate here, right? So that would be pretty strong evidence. We could interpret that as pretty strong evidence for the alternate hypothesis relative to the null. Alternatively, we can take that 13.89, we can subtract 1 from it and say that our alternate is about 1,289% more likely than the null hypothesis, if we wanted to talk about this in percentages, right? So if you think about this in terms of, if I've got 2-to-1 odds, right? This is saying that my event is twice as likely to occur as sort of this other thing, right? I could also say that sort of my event is 100 times more likely than my alternate event, right? So we're just taking that odds and subtracting 1 from it, and then sort of we can interpret that as a percentage. Okay. All right, so we're feeling pretty good about P 0.005, right? So we're saying this is pretty strong evidence against the null hypothesis and for my alternative based on what we've got going on, right? But if we go back through and take a look at our probability, even at P = 0.005, there's still about a 6.7% chance that the null is true, assuming that the null and the alternate hypotheses are equally likely. Okay? And so if we go, so if we know that our odds, or the probability of event, is our odds over 1 plus the odds. So if I take 13.89 over 13.89 plus 1, what does this give me?
0.93.
What's that?
0.93.
0.93 what?
284.
0.93, call it 4. Okay. So this, I could say that on the best case scenario, the 93.4% chance of the alternate relative to the null, right? If I take the inverse of that, if I take Q, this is 1 minus 0.934, that's still giving me 0.067, right? Or at least it's whatever I calculated up there. Yeah, right? So even at that level, still about a 6% chance that the null is true, assuming again the best case scenario where the null and the alternate null hypotheses are equally likely, right? So wanting to be careful and thinking about our statistical models and our results in terms of strength of evidence, as opposed to just is this statistically significant, is it not significant? And so again, our base factor bound, what we've calculated here is the strongest case for the alternate relative to the null. The very, very best case scenario, the peak of this, right? Our base factor can get no bigger than this. Probably the likelihood of the alternate relative to the null is less than what we've actually calculated here, but this is our best case scenario. And so again, at 0.05, the likelihood of our alternate hypotheses is only about 2.5 times that of our null, best case scenario, right? So again, talking about how, if we're thinking about this in terms of strength of evidence, how our cutoff of 0.05 is actually not super strong evidence for sort of what we'd like to think it would be, which is disappointing, right? And I'm not suggesting that we go through and start changing around our criteria for what we're going to call statistically significant or not, but this whole argument for augmenting how we're talking about our statistical analyses is being more realistic in terms of what it means and what it doesn't mean, and then building inferences from there. That's not to say, and again, if we were to say, oh, now everything has to be 0.001 before we can publish it, that's actually bad. I wouldn't recommend that, right? And that's going to cause even worse problems like we've already talked about. It's just thinking about things in sort of more flexible terms than, is this a real thing or is it not a real thing? How are people feeling about base factor bound here? Chris, you're looking skeptical. What are you thinking?
Just trying to catch up.
Okay, yeah. We're going to go through, and in the examples, and this is what I'm doing, is trying to go through and incorporate some of this stuff so that we can see how we might go through and use this and interpret this in a couple of different contexts. Okay. All right. Also, this is a weird thing, I just figured this out. If we start to get p-values that are greater than 0.50, it actually flips this around, so it kind of screws things up. But at the end of the day, if you've got a p-value of greater than 0.50, I wouldn't be calculating this stuff anyway. I mean, we're nowhere near interpreting anything as sort of evidence against our null. So, but just know if you were to try to calculate base factor bound for a p-value that was greater than 0.50, like 0.85 or something like that, it tips it around and talks about evidence for the null as opposed to relative to the alternate. Okay. So just in terms of odds, sort of trying to get, because as I was thinking about this, like, okay, well I got say 12 to 1 odds for the alternate versus the null. Is that a lot? Is it a little? And so just try to come up with some examples, some like actual practical things, and sort of games of chance are actually any sort of people who play cards, dice, gamble, anything like that, ish. Okay. If we're thinking about the odds of rolling, you've got dice, right? So a single die, right? Six-sided die. We're not getting into D&D stuff here, right? I just roll a value less than or equal to 3, right? Six-sided die. There are 3 numbers that are 3 or less. 3 numbers that are greater than 3. So the odds of rolling a 3 or less are even odds. They're 1 to 1, right? It's a coin flip. Rolling less than a 4, 2 to 1 odds, right? There's 4, 1, 2, 3, 4. So the odds of rolling less than or equal to 4, equal 4 to 2. 4 ways I can, 4 numbers that I can roll that are less than or equal to 4, 2 that aren't. That translates 2 to 1 odds, right? The likelihood of rolling a value 4 or less are twice as likely as rolling something that's greater than 4. Rolling 5 or less, 5 to 1 odds, right? You've got 5 numbers that are 5 or lower. 1 number that's less, we've got 5 to 1 odds here. Okay, so if we're going through and we're thinking about, all right, so if you look at a base factor bound, so like the odds of rolling, odds of rolling a 5 or less with 1 die are 5 to 1 odds. Is rolling a 6 a weird thing to happen? No, it happens all the time, right? We look at the base factor bound for p equal 0.05. Your base factor bound, the evidence for the alternate relative to the null are at most about 2.5. Comparing that to rolling sort of a 6 on a dice, this is not an uncommon thing, right? Showing sort of the weakness of our evidence against the null or our evidence for our alternate hypotheses of p equal 0.005, right? If we're drawing cards, if I want to draw a card that's not a spade, about 3 to 1 odds, right? So I can draw a diamond, a heart, or a club. So they're not a spade, so there's only 1, right? Drawing a card that's not a base card with ace, not a base card if it's not a jack, right? Drawing a card that's not an ace, 12 to 1 odds. So if I just go through and pull a card out of the deck, is it likely to be an ace? Nope. I'm actually 12 times more likely to pull something that's not an ace than it is an ace, right? And so if we're thinking back to our base factor bound of about 13, right? This is close. But if I did draw an ace, should I be shocked? Probably not, right? It's not terribly uncommon, right? And so just wanting to sort of match this up. Same thing for anybody play poker? Okay, 5-card stud. If you're not familiar with poker hands, this might be, but odds against a pair, odds against 2 pair, 3 of a kind, straight flush. By the time you're getting 4 of a kind in terms of a 5-card stud, just 5-card hands, it's incredibly like that just doesn't happen. That'll happen for every 1 time it happens. You were expecting 4,165 times that it doesn't happen, right? Those are very, very, very slim odds, right? But if we start to look at, again, when I'm talking about reporting p-values as actual and not just cutting things off at p less than 0.001, if I'm, say, here, peak 0.001, my Bayes factor bound about 53.26. But if I go to 0.000 down here, this is a t-statistic of 4.9. I mean, these happen, right? This is much a different outcome and strength against evidence for my alternate than this, right? And so this starts to become sort of, I think, a good argument for trying to develop ways to actually give precise p-values that doesn't take up 7 lines of text. You've got it stacking a bunch of zeros on there, right? But it starts to become important because this is a much different strength of evidence result than that is. So kind of getting the idea of odds and sort of how we sort of might use these to think about some of this stuff. Okay. So we're going to go through and work through sort of incorporating these in terms of our interpretations, and we'll start to see if we can come up with more involved and nuanced ways of thinking about what our data are telling us. But another thing we want to think about is, remember that through all of this, right, our statistical tests are based on the assumption of perfect scenarios where we don't violate assumptions, where everything's sort of, we have random samples and everything is done, we're measuring without error and things along these lines. A lot of that stuff we know is not going to be the case, and there's not much we can do about it. But some things that we can take a look at in terms of our assumptions of our data. If we're going to run a single sample t-test, I'm going to be comparing my data against some reference value. But I'm assuming my outcome variable is an approximation of a continuous variable. And now, we in psychology will use ordinal scales with 5 or more values as continuous. It's not even close, but when we look at evidence, there's some evidence that suggests that we're probably not losing too much as long as we do this. I know Kyle does some stuff on, we're talking about scaling to, we got a scale, and I actually make a mark on the scale and then sort of measure it.
Visual analog scale.
What's up?
Visual analog scale.
Yeah, a visual analog scale, right? A VAS is going to be an actually true continuous because I can mark that at any point along the scale. That's usually, I mean, we may have marks of 0, 1, 2, 3, 4, 5, whatever, but we can actually start to use that as an actual true continuous measure as opposed to sort of our ordinal scales. But as long as we have something that's not categorical, nominal, we're generally fine-ish, okay? Also assumptions, we have to assume that our observations are independent. That means tomorrow's answers don't depend on Alicia's answers, don't depend on Siley's answers. Everybody's data is independent of one another. The big thing we're concerned about, and sort of our underlying assumption of our t-test, is that the distribution of sample means for the population is normal. Okay? CJ, if I say an assumption of the test that the distribution of sample means for the population is normal, do I care about what the actual distribution of my data look like? Ish, kind of, right? But only to the extent that I can infer something about the distribution of sample means from the sample data that I've collected, right? And we know, if you think back to previous information, under what conditions does Chris, under what conditions does the distribution of sample means start to become normal?
You get enough of them.
Okay, as my sample size starts to increase, right, distribution of sample means quickly becomes normal, and then what else? Anybody else remember the other condition in which distribution of sample means starts to become very normal quickly? When the population, or when the distribution of whatever I'm measuring in the population is normal, then it starts to become normal very quickly as well, right? So if I'm looking at height, right, even if I have a sample of 10, distribution of sample means for all samples of size 10 still becomes normal very quickly if the distribution of the population is normal, right? And height has a normal distribution of the population, then I'm going to be fine, right? Now, if I'm looking at acts of aggression on the playground, that's not going to be normal. Distribution of aggression is going to be very skewed, right? And so that's problematic unless I have reasonable size samples. If I have sample sizes of 20, 30, even still, even though the phenomenon I'm looking at is skewed, the distribution of sample means it's still going to start to become normal. So when I'm looking at my data, right, I might be, if I'm looking at substance use stuff, I might expect a skewed distribution. If I don't get a skewed distribution, that's kind of weird, right? But as long as I have reasonable size samples, my distribution of sample means it's still going to be more normal. My sample data is skewed. The distribution of sample, my assumption of my test isn't about my sample data, it's about the distribution of sample means. And as long as I have a reasonable size sample, I should be fairly robust to some stuff here, okay? So what we're wanting to do is, even though we want to make sure that we have a continuous outcome, we want to make sure our observations are independent, and then we're going to be interested in looking at our distributions, but only to determine the extent to which I can say it's reasonable to expect the distribution of sample needs to be normal based on the sample that I've collected and things like that. One thing we do want to make sure is we don't have weird outliers or extreme data. This starts to get tricky, right? Because there is no universal definition for an extreme value or an outlier. It's going to depend a lot on what you're measuring, whether or not sort of this observation is part of the intended population, the size of your sample, how far it is, right? Anytime you see anybody engaging in just like rigid cut point, if it's over this, it's an outlier. If it's not, it's not. That's the wrong way to go about this. It's a methodological thing. You have to go through and think about your data as a whole and make arguments for this is something that, yeah, it's not great, right? But I've got a big enough sample that it's not going to drag things around too much, right? If I've got a sample of 200, my one person hanging the hell out here is probably not that. If it's someone who's a reasonable or real case, probably want to keep it in, right? Now, if I got a sample of 20 and I've got someone way out there, then we might need to do something different with that, right? So just wanting to make sure that we don't have something that's going to unduly impact our results. Yeah.
If you're looking at like sample graphically, is it fair to go through and exclude people if you can visually see like this person is so far out, like it exceeds whatever, like 3 standard deviations? Can you say?
It kind of depends, right? And I mean, so there's this balance between sort of statistical purity, right? And so you'll hear about procedures using trimmed means and things like that, right? That's saying that anybody on the high end, the low end, we're going to get rid of those, right? And we're just going to look at what's going on in the middle. And there's arguments for using these types of statistics. But for a lot of us in clinical psychology, what we're doing, if you start cutting off the people on the high and low ends, you're systematically eliminating the people you promote most interest in, right? And so that starts to become problematic. And when we look at the efforts to systematically exclude those cases that are on the high and low end, it looks like a lot of times it causes problems and biases in our data. We're actually worse off for excluding them than just leaving them in, right? Now, what I would say is there are different philosophies on how to go about and do this. And one camp says you have to go through, make all your decisions operatory, screen the stuff beforehand, and then what you decide is what you decide. That's it. There's no more mucking around with stuff. And that's kind of a purist approach, and I think there are good arguments for that. But the counter argument is, and particularly when we get into some regression stuff, well, I can't do a proper screening unless I run the analyses, right? And then if we're thinking about sensitivity, robustness of our results, if I have results that either appear or go away with the exclusion of 2 or 3 people who are just kind of on the margins, that starts to make me worry about how robust my results are, right? Now, if I've got someone who's way out of bounds, right, and it looks like going through hard copies, it looks like maybe this person completed the survey in 2 minutes when everybody else took 15, I would say, I don't think this person took this seriously and I got rid of that person. Or if this person, based on their characteristics, is not part of the population I'm interested in, we get rid of that stuff. But if they're kind of on the bounds, even graphically, and I'm glad you brought that up because we're going to use a lot of graphical methods, and maybe I see someone who's kind of there, and then their score is kind of off, sort of in the distance. What am I measuring? How far are they out? How big is my sample? Even though we go through and it'll want to identify and characterize our sample and say, okay, we've got some stuff with maybe some unique cases within this data set. Unless we have strong evidence to get rid of them and can make strong arguments, but generally your best bet, I went through and threw out 10-15% of my sample because they were outliers. That suggests to me that you threw out anybody who didn't do what you wanted them to do, and then that starts to become problematic, right? So if I'm doing, so like say a film manipulation, right, when I'm showing people, so this film is supposed to make them sort of laugh or something like that, and I systematically go through and throw out the people who said they had negative reactions to that, make an argument and say, well, these are the people who manipulation didn't work for, but I'm also sort of taking out the people who sort of didn't do what I would do. It starts to shift things around, right? If I'm doing a reaction time task, I'm going to take someone 3 seconds to do something everybody else is doing in like a quarter of a second, then let's get rid of those people because they probably sort of weren't paying attention. And so this is why the screening piece is so difficult. One, you have to know your data, and you have to be thinking sort of more generally about how to go through and put this stuff together and what makes sense as you're working through this stuff. And so we'll go through, and this is hard, right? So I give you screening stuff to do and sort of a general framework. But if you're not haven't done a lot of screening before, I'm looking at, I don't know if this is weird. Is this weird? Is this not weird? What do I do with it? As we start to go through and you start to see more data and say, okay, this is kind of what data will look like, real data will look like, you start to get better at picking things up. But again, anytime you would go through and exclude somebody, you would just want to have a really strong justification for why these cases specifically, we got rid of them. Other questions on this stuff? Okay. In addition to our formal assumptions, we've got all these other assumptions. We always need to be thinking about this. Keep these in the back of our minds, right? So if I'm looking at my own research, evaluating other people's research, thinking to what extent are the data in keeping with these auxiliary hypotheses, and they'll never get all of these, but then the question is to what extent does this impact my results, right? If my data aren't truly, it's a convenient sample, which it's always going to be, does that impact my results or does it not? And not just does it impact, but how does it impact? Do I think this is going to, if we were to get a truly random sample, would that make things sort of increase my effects or decrease my effects, right? Thinking about some of these types of things. Okay. So, example that we'll run through here. All right, what do we got? Okay, good. We'll get through screening at least. All right, so I want you guys to go through and pull up your, in SPSS data set. It's going to be single sample t-test. And sort of hold on to that handout that I gave you that has a single sample t-test screening. So what we've got is a measure of interpersonal difficulty, IFP32, self-report measure intended to assess domains of interpersonal difficulty. Scores range from, total scores range from 0 to 128 with a mean of 25, a representative sample of 800 adults. So I pulled this from the manual, okay? Normative sample was 50% female, 77.7 white non-Hispanic, age ranges 18 to 72. Over half the sample, just over half the sample, less than or equal to high school education, sort of moving on up. What we're interested in is we're interested in the effects of stress exposure on interpersonal functioning. So what we've done is we've collected IAP32 data from university undergraduates, a large sample, 405, reporting distress in response to exposure to a prior trauma. And so our sample, 77% women, so much higher percentage of women, about the same white non-Hispanic, but also considerably younger and more educated than the normative population. Okay. So what we're going to do, so in a sentence, state the null hypothesis being tested. Nick, can you give me the null? What's the null hypothesis that we would be testing sort of in this problem here? So I guess it's not super clear. would we, or in general, and not being a trauma researcher, would we expect people exposed to reporting stress in response to prior trauma, would we expect them to have sort of greater levels of interpersonal difficulties in the normal population or less interpersonal difficulties? Greater, right? So given sort of the single sample t-test, can you give me can you put into words what the null hypothesis is that is being tested here?
So those who have experienced in the population that have been exposed to prior trauma are expected to have this score greater than 25 on this inventory of interpersonal problems
Okay.
scale.
Perfect, close. Not greater than 25, I mean, that's our alternative hypothesis. Statement of the null is, yeah, the population of university undergraduates exposed to prior traumatic experience expected to have an IIP score equal to 25, something like that, right? Because it's our statement of the null. Nice work pulling in the population on that. Null and alternative hypotheses, and then we've got some other stuff here. But what we're gonna do is we're gonna go through and actually start screening if SPSS opens up. So, who here has experienced SPSS, has worked with SPSS-ish? Okay. I'll go through, Alicia, you're kind of stuck because I'm going to have you doing stuff in Stata as well. You're going to be sort of bilingual in terms of this, which will be good. And I will have some stuff for you on that, but I also have just a general tutorial about SPSS, sort of setting up data sets and things like that. I'll just give you all a link. You can find that and work through those if you like, just as a refresher. So what we're going to do here is we want to go through, and first we want to screen our data to make sure that our data are consistent with underlying assumptions of a single sample t-test, okay? So what I'm going to do first, if we've got, here we've got participant, we've got gender, age, ethnicity, and then a bunch of individual subdomains of the IIP 32. Are we interested in any of this stuff? Not really, right? Our main test is going to be this IIP total score. If you go down here and click on variable view, and look at your labels, this just tells you sort of what all the variables are. On values for gender, if you go through, you see zeros, women, one's male, right? So we can go through and see our stuff here. Now in SPSS, first thing we want to do is we want to look at, and I'll give you a handout to try and give you some guidelines for working through some of this stuff. First thing we want to do is we want to look at accuracy and plausibility of our data. We want to look for missing data as well. And an easy way to do this in SPSS, if you go over to IIP total here, and we right click, see sort ascending, kick that. And what this is going to do is it's going to go through and it's going to sort. So your missing data is on top and then everything down there, okay? Chris C., what are we seeing going on with these data?
They're like 70-ish missing data.
Okay, so in this case, in this larger set, we've got 70 cases. We've got 70 cases with missing data. This should trigger alarm in us, right? In a sample of 400, what is it, we say 405, you're missing 70 cases. That's a big chunk of data, right? So this is something that I would definitely write down and sort of want to keep account of, like, okay, what's going on with this? Now, I know, because these are my data, and I collected them, I just wasn't collecting these data when I started the project, so I've got a good reason why these are gone. But if I didn't know this, this would be something that I would want sort of make note of. But, so all of these cases are not cases that I'm going to be interested in because they don't have total. So what I'm going to do is I'm going to go through and I'm going to highlight those, right click and hit clear, and just get rid of those, okay? And what I should have done first is go to File, Save As. I can impress upon you the importance of never working with your actual running analyses on your actual sort of your primary copy. Always, 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 always save some sort of working file or scrap file, because as soon as you delete a bunch of stuff and then save it, you've screwed everything up, right? So I should have done this before I deleted all those cases, but I'm going to go through and I'm going to hit save. I'm just going to call this scrap. That's just my notation for like working sets and things like that. So now I can do whatever the hell I want to do with this. It's sort of not going to ruin anything, right? So I've gone through, gotten rid of all of my variables or all my cases of missing data. But now to sort of mark down the number of cases that I have missing data for. Also, though, because this is my outcome, I want to make sure that values are in range, right? Sally, what's the range of my IAP total score? It's on your. It's in the little red box.
0 to 128.
0 to 128. So I've gone through and sorted this in order. So I can go down through, and I see down here at the bottom, I've got a 999 code, right? Now for my data, I use 999 as a missing value, right? But if I go through and look at my variable view, I don't have a missing value here, right? If I wanted to do that, if I want to go to missing, click right here. I say discrete 999, and I hit OK. SPSS will treat these as a missing value, right? So I can assume that what this is probably is someone with missing data, right? And I see that they're missing subscale scores. Probably this is a case that I couldn't calculate a total score for, and I had entered 999 to indicate that so that was missing. I think probably what happened, but again, at the end of the day, it's not an actual case or an actual value that's reasonable. So I would mark that down, say case number 414 had a unreasonable or a value that was out of bounds, mark that down, and then I'm going to go through and clear that. So at this point, because the only thing I'm interested in is my IAP total, I've gotten rid of, I had 70 cases with missing data, so I marked that down. I had one case that had an out of bounds value, so I marked that down. So I'm left with a working set of 334 individuals. Okay? So now what I've done is I've gone through now and addressed accuracy, plausibility. What I can do is now go down through and start looking at sort of different descriptors and things like that. So again, if you have your single sample T screening worksheet here, have that. This is just working through all the steps that we're going to do here. The first thing I want to do is I want to take a look at my descriptive statistics and my skew and kurtosis, and also saving Z scores for my individual cases. And so what I'm going to do is I'm going to go to Analyze. We go to Descriptive Statistics. I'm going to go to Descriptives. You can follow me? And click on that. And now the only, because this is simple analysis, I'm just interested in my IAP 32, my total score. So I'm going to move that over. Then I'm going to go to Options. And I'm going to request skew and kurtosis. Right? SPSS doesn't give these by default, but we want to get our skew and kurtosis values. I'm going to hit Continue. And then the last thing I'm going to do, you see this box that says Save Standardized Values as Variables. This is just going to go through and calculate a Z-score for my for every case based on their IAP 32 score. Why might I be interested in Z scores, CJ?
See how far the scores are from me. So
Yeah.
it varies.
And so how far from mean? So what can I use with these Z scores to start to look at? Any ideas? Okay, you got some distribution, you got some skew stuff. What specifically, and so you're right, so Z-scores give me a standardized distance for the mean. What might this be helpful for in terms of sort of teasing apart? extreme values, right? If I've got a case that's 4.5 standard deviations from the mean, they got a z-score of 400.5, I think, oh wow, that's pretty extreme. Now, my sample is really big here, right? I've got 334 people. So am I gonna be super worried about, am I gonna be super sensitive to extreme values here? Probably not terribly so, right? I've got a big enough sample that's probably gonna handle this, but still gonna go through and keep these. So, I've got my variable in here is hitting save, gonna hit paste. Okay. Who here has worked with syntax files before? Okay, 1, 2, nobody else? Okay. This is gonna be, SPSS is kind of the standard program used for psychological statistics. But the criticism of this and sort of other areas, people like, well, you go through a bunch of garbage with your pull down menus and have no documentation of what you've done, right? Your syntax file is what's gonna keep you sort of on target, and it's actually gonna make your working with stuff much, much easier. Once you get some screening procedures down, you have those saved in the syntax file, then you just go through and start changing around stuff in your syntax file. It makes things much, much easier. Now the downside to SPSS is the programming language is kind of a pain, but what we can do is we can work through our pull-down menus, and we can go through and use the pull-down menus, paste in the syntax file, and keep a record of stuff. One thing you might want to do, and this I would strongly encourage you to do this, if you go down through and you hit asterisks, right? You go through asterisks, I'm going to say, I can write notes to myself, right? A couple of asterisks, one asterisk works, I use two, so I'm putting it up to you, right? But what this is, you can go down through and start annotating your file so that you can remind yourself what the hell I was thinking, what I was trying to do as I was going down through and doing this, okay? So once I've gone through and pasted this in, if I take my command, I highlight it, and then go up, hit my green arrow, and run this, this is gonna give me my descriptive statistics here, okay? And so if I go through and I take a look at my descriptives, someone tell me, tomorrow, what are you seeing here in terms of your descriptive statistics?
The lead is on the lower side of the range.
Okay,
Large standard deviation.
okay. Skew looks fine. How did you determine, I agree, how do you determine that skew looks fine?
There was a number of called earlier.
Yeah. Threshold, the rules of thumb for skew and kurtosis is less than or equal to 2, right? Do not use this as a sort of bright line determination of anything, right? And don't say that things that have a skew of less than 2 are normal. As we go through and look at things graphically, you'll see that it's absolutely not normal, right? But these are general guidelines for what people will start talking about in terms of things that start to become problematic, right? So here we have a skew of 0.187, which is really nice. We have kurtosis of negative 0.6. So what does negative kurtosis look like? Anybody remember? Yeah, exactly. Kind of boxy, square, kind of square distribution. Slump shoulders, kind of boulder looking like, as opposed to positive kurtosis has that narrow peak and kind of flat wide tails. Kangaroos, that's right. So platypus and kangaroos, right? So looking at my descriptive statistics here, I'm seeing my min and my max, and I went through and so just checking, but my min and my max all within bounds for this measure. 0 to 99, that's looking fine. Total scores, I'm not missing any scores here. My mean and my standard deviation, not too worried about that. Looking at my skew and my kurtosis values, both of these look like they're well within bounds of what would be reasonable given normal data analysis. Okay, so I'm feeling pretty good about this. So what I'm going to do now is I'm going to go through and I'm going to do some graphical stuff. So I want to go through to graphs, chart builder, and said okay, let's go through Okay, so what I want to do first is look at a histogram. So if I go down and I choose histogram here, and they give me some different options, I like this one. I'm going to pull it up in my file here. Looking in my window, I want to go through and run here. And there's a number of different things that you can do sort of with this. We won't worry about it because we just want to get a general sense for the distribution. Okay? Everybody got to this point? Okay. And so then what we can do is we can go through and paste this, and we'll see that this syntax command is huge. You couldn't probably just do this by memory unless you've been doing this forever and ever. I'm going to go through and say, looking at histogram, right? So I know what I'm doing here. And if I go through and I highlight and I run this, it gives me a histogram of my data. Alicia, what am I seeing in terms of this histogram for my IEP 32?
Somewhat normal?
Yeah, right. I would say this data, so this figure, the histogram looks relatively symmetrical. I mean, it's not perfect, but it's relatively normal and symmetrical. Anything distinctive about this histogram that I might touch base on, Chrissy? There's not anything super big right there. I might make a note of this. I got one value that's, and I would identify this as it looks like a case that's falling away from the rest of the distribution, at least how SPSS has sort of been this histogram. So I may make a note that the histogram of IEP 32 scores are relatively normal and symmetrical with one case falling away from the larger distribution, right? So speaking to your point, Chris, now if this was way out here,
I'd exclude them.
then maybe I would I'd want to see if that was what was going on with that case. In this case, I'd probably think that maybe someone just went through and like maxed out on everything, and I might have questions about sort of the reliability of their data. This is just kind of, and with a case like this, or with a sample of this size, what we have 334, a sample of 334, I'm going to get some people out there, right? I expect to get some values that are pretty extreme, right? Now that's just probably me catching the ends of the distributions. But again, with a sample of 334, I'm pretty robust to the types of outliers I could have. Even what the maximum scale is 128. Even if I had someone probably close to out here, I might consider keeping them in, just as long as I can verify that they weren't screwing around with all this stuff. If they're screwing around, then we can pitch them out, right? But it just looks like, if I look down through the case and other stuff, it just looks like this is someone who's incredibly severe. I might say, well, this is just kind of behind the distribution capture. Okay. So histogram's looking okay. Let's go to analyze, or excuse me, graphs, chart builder, and now let's go through and take a look at a box plot. Choose box plot. We've only got one variable we're looking at, so we'll pull that up. And the same, it looks like it kept IEP 32 score in there, right? So we can take this and drag this over if it wasn't there. Right? So we can do that. And then if we hit paste, go through and take a look at our box plot. Here's our box plot. Anything interesting going on with our box plot? No, right? This is symmetrical. Median value just a little above 40. Sort of min, max, no values extending beyond 1.5 times your quartile range. Right? So that it would be reasonable, maybe a little bit higher sort of stuff on the high end and the low end, but I would might describe this box plot as relatively symmetrical and otherwise unremarkable in terms of things that are going on, right? And so then the last thing that we could do then is we're going through, remember that we had asked SPSS to save Z-scores, right? And if we see down here, we see Z IIP total. This is just our Z-score of our IIP. So what I did is I took my descriptives statement and I copied that and I pasted it down here, right? What I can do is, because SPSS, when I save Z-scores, just takes my variable name and just adds a Z in front of it. I can say, all right, SPSS, I want to look at descriptives, and I want to look at the Z-score of my IIP total. I'm going to erase this save command, because save is just telling it to create Z-scores. I don't need to Z-score my Z-scores. So I'll get rid of that. If I go through, run this is going to give me my descriptives, right? And here, I'm just looking at my min and my max, right? So at the low end, I have a case that's about 2 standard deviations below the mean. I've got, at the high end, I've got a case that's about 3 standard deviations above the mean, right? Am I concerned about extreme values in this case? No, right? I mean, again, if I go back up and I take a look at my, I've got a case that's kind of hanging out there toward the end, but this case is just a little under 3 standard deviations above the mean. That's pretty extreme value, but given the size of the sample, that's not problematic. That's not going to have any consequences, anything along those lines. So in general, I'm going to say that aside from those 70 cases without data, we'll need to know what's going on with that, right? But if I can account for that, these data are relatively, there's no problem with sort of underlying, at least from data assumptions in terms of looking at this stuff. Questions on any of this stuff? Okay, cool. What we'll do is we'll pick up on next week, go through it, and it'll take us like 2 seconds to actually run the t-test. Spending time going through screening, cleaning your data, sort of noting also the weirdness and all that stuff is going to take, in any situation, is going to take far more time than actually running your analyses. This will constitute hours of your life when you're working with your own data. Actually running the analyses will take 15, 20 minutes at most, right? But important that you, one, know what your data are doing, whether or not you're violating assumptions, things along those lines. And then as you're going through, making sure that you save your syntax file, right? Just save that, this is documented, and that way next time you come into your data, you don't have to start all over again. You've got a record of what you've gone through and done, and once you start to get pretty good at this, you'll understand these syntax files. You can take the stuff I did from last week, just paste it in this week, and just change variable names, you go through and start running things pretty quick. All right, folks, nice work.